Okay, this is sort of why I was hesitant to work out bending moment at each part of the cut by hand with reactions, because there's a relationship between the two, and it's sort of similar to what we've just seen. I kind of don't want you to read all this. It's just a lot of equations. Yeah, okay. So once you learn how to draw your shear diagram, you can draw your moment diagram from the shear diagram. So you can look at the total shear, so the total loading inside of the beam at a distance. Okay? So loading at a distance is moment. So let's just do a new example. 13.6. Okay, so this is point C, A, and 3 meters in, there's a B. 1 meter away there. There's a load here at B, 40 kilonewton. Okay, so right away, what needs to happen? Need my reactions. So I've got a reaction at A in the Y. I've got some sort of reaction at C in the Y. Okay, and here we are with 3 meters to 1 meter. So right away I can see that my reaction in C should be a lot higher than reaction in A because they're closer. And I can prove that with my moments. Let's take it about A. So 3, so this is going to be negative 3, 40 kilonewton, plus 4 meters reaction C. Reaction C is going to be 3, 40, 4. So it's going to be 10, it's going to be 30. So that means my reaction at A is 10. Okay. Oof. So now I know my reaction. 10, 30, 40. Okay. So now I want to construct a shear diagram from that. And then I'll show you the relationship and how to get the moment diagram. 10, 40, 30. So same process. And after you do this a lot, it will be intuitive. So I'm going to 0, 0, 0, 0, 0, suddenly hit 10. So let's call this 10, positive. Now nothing happens all the way until you hit this 40. And so that's going to subtract 4. Okay? So now we're at negative 30, 10. And now nothing happens until you hit this 30. And boom, takes you back up to 0. Okay, so this is my shear as a function of distance. And this was what, 3 meters? So 3 meters, 1 meter. So all throughout this beam, you can tell exactly what the shear is at any point. And so if it was going to fail due to shear, where would it be? It would be down here, since shear is force over area. So this would be your 30 over some cross-sectional area in the beam. Now, moment as a function of x is similar to some of the things we've seen in class to this point. So moment out here at the support, it's a rolling joint. So it starts at 0 at both supports. In this case, there is no moment reaction from the supports. So I know both of these points start at 0. Now, say we go 1 meter ahead, and this is 3 total. So say we go 1 meter ahead. So now you want to consider your cut. So inside of the beam, after 1 meter, there is a shear of 10. Some sort of shear force here. It's positive, so I need to draw it downward like that. So 10 kilonewtons. And this is 1 meter away. So my moment at 1 meter is 10 kilonewton meter. Okay. So then at 2, it's still negative 10. No, it's positive 10, sorry, downward. 2. So now, after 2 meters, it's 20 kilonewton meters, okay? And as you travel to 3, so we're at 30, 3 meters. Positive. Okay. And then it's discontinuous here. So where this crosses 0 is a local maximum for moment. And then this guy. I would like to consider it from this direction. So after 1/2 meter, let's say 1/2 meter, we've got negative 30 shear in the beam. So 1/2 meter this direction, we're going to be at 15. Okay, so where's 30 at? Let's see here. So we're going to climb slowly up to 30 and then abruptly down. And I know these 2 points are 0 and this is my local maximum. Sorry, these are at the same spot. 30 kilonewton meters, like that. And if you look here, the relationship between these two is you're doing the area. So if you take the total area here, it's 10 kilonewtons times 3 meters. And this one's 1 meter times 30 kilonewtons. And so at each point, you're only looking at a small area here to find this point. And then you're looking at this area to find this point. And it correlates down to where you're cutting your beam. Okay, let's do another example.